Okay. Now in this session, we will have to discuss one interesting gate, and it is XOR gate. Now sometimes it may be written as EXOR. Any word is there, but this is a convention to write the XOR gate. Or sometimes it is maybe written as XOR gate. Okay. Now this gate is a very important gate, and it has the application potential. Now, what is the XOR gate? Typically, we are aware about the OR gate. Now, for better understanding, I will think about the 3-input OR gate. Okay, therefore, we have the 3-input. 3-input OR gate. I will cancel it. This is 3-input OR gate. Bubble should not be there for OR. If it is bubble, then it becomes NOR gate. Okay, let it be 3-input OR gate. Inputs are A, B, C, and output is Y. Along with this, I will think about the 2-input OR gate also, because we will have to write the logic equation for 2-input OR gate. It will be simple once we understand what is the OR gate, what is the XOR gate. Now in case of this, if I will have to prepare the truth table for the normal gate, I will prepare a truth table in this fashion. This will be the input. Here it is input. This is output. Now there are 3 inputs. Therefore I will write it is A, B and C. The output is Y for the 3-input OR gate. And possible combinations are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. I will have to amend it. Then it is 1, 0, 0, 1, 0, 1, 1, 1, 0. And the last stage is 1, 1, 1. These are the 8 possible combinations. Now what happens for typical OR gate? For typical OR gate, it becomes 0 and remaining OR 1, 1, 1, 1, 1. Because what is OR? OR of A, B, C means A or B or C. If any one of them is 1, then the output is 1, and only for A is equal to 0, B is equal to 0 and C is equal to 0, output will be 0. This is the normal OR gate. But suppose here I will write this is for OR gate. But if I think about the XOR gate, now the symbolic representation is this. This additional line indicates that I am going to exclude certain combinations. Which combinations I am going to exclude? And therefore, instead of preparing one more table, I will write this is output for XOR gate, or I will write XOR gate. It is output Y. See, the interesting thing is that those combinations from input are excluded. Check, those combinations from input are excluded for which even number of inputs are 1. Gaman baga, even number of inputs are 1. Therefore, typically I can focus on this. Here you will observe that this and this 2 inputs are 1. Therefore, what I will have to do? I will have to exclude this case. If I go here it is 1 and 1. Therefore, A and C are 1. Therefore, even number of inputs are 1. I will have to exclude this case. Here I will have to exclude A and B are 1, 1. Therefore, I will have to exclude this. But I should not exclude this because 1, 1, 1, 3 inputs are 1. And hence, the output will be 0, 1, 1, 0, 1, 0, 0, 1. Therefore, for 0, 0, 0, output will be 0. For 0, 0, 1, output will be 1. For 0, 1, 0, output will be 1 because it behaves as a OR gate. But for 0, 1, 1, if it is behaving as a normal OR gate, it should be 1. But as it is excluded NOR gate, it has to exclude certain stages, it is 0. Certain cases. Which cases are to be excluded? The cases for which even number of inputs are 1. Here 2 inputs are 1. Exclude this. For 1 0 0 it is 1, it remains as it is because 1 is there, 1 0 0, but odd number of inputs are 1, therefore, and this is the expression or truth table for EXOR gate, XOR gate. This is symbolic representation, this is truth table. Now, same truth table if I will have to write for 2 input XOR gate. I have made the XOR gate. How? I will write here it is input, correct? Then I will write it is output. Under the input there are 2 combinations. I will write AB. Here the output is Y. Now only there are 4 combinations. Therefore it is 0 0 0 1 1 0 and 1 1. Okay. What I will have to do? I will have to write 0 0. It will be 0. 0 1 it will be 1. 1 0 it will be 1. And 1 1 it will be 0 because I will have to exclude the case for which even number of inputs are 1. If the 2 input 1 hai, exclude that and that is equal to 0. Correct. Therefore, this will be the truth table for 2 input XOR gate. Now, why to consider such situation? Obviously, you may think about suppose there are 3 inputs are 1, then I will have to exclude. In this case, only last stage is to be excluded. I can define my own rule. But whether this rule or whether such type of gate has certain application potential, then it will sustain for a long time. And therefore, this XOR gate has the application potential. Now, what is the application potential? We will discuss in next video. Typically, if I write the equation y is equal to a and b complement or a complement and b, then this will satisfy our truth table. Check. Suppose a and b both are 0 0. Then what we will do? If it is 0, then irrespective of this term will be 0 plus, that is OR, as b is 0, irrespective of this term is 0, 0 plus 0 will be 0 and it will satisfy this. If it is 0 1, this is 0, therefore this will vanish. But as it is 1 and a is 0, therefore a complement is 1, therefore 1 and 1 it will be 1, 0 or 1 it will be 1. This condition is satisfied. For 1 0, this will be 1 and this will be 0. You can check later, and therefore 1 or 0 it will be 1. It is satisfied. And for 1 1, this is 1 but this will 0 because b is 1, complement of b will 0 and hence this will vanish, it will 0. A is 1, its complement is 0, therefore though b is 1, a complement is 0, therefore this will 0 and finally output y is equal to 0. Therefore this can be treated as the logic equation for XOR gate, 2 input XOR gate. Hence typically I can say that this is the 2 input XOR gate symbol, this is 2 input XOR gate logic equation, and this is 2 input XOR gate truth table. Now, how we can implement? Now, in the last video we have observed that the NAND gate behaves as a universal building block, and therefore only with help of NAND gate we can construct all the possible gates. It should be true for the XOR gate too. Therefore, I will give you one circuit and then we will try to implement that. Correct? Therefore, what is the circuit for implementation of XOR gate using NAND? First of all, I will draw the circuit. Correct? And then we will discuss on that. Remember that if I will have to think about the XOR gate and if I will have to implement that XOR gate, then finally it should happen that the output should satisfy the conditions which are applicable for the input. Therefore, it should satisfy the truth table, expected truth table for XOR gate. I will draw the circuit first and then you will realize or you will observe that it is very interesting. This is the circuit diagram or the block diagram for the implementation of XOR gate. I will begin with this and then we will uh, go through an interesting situation. Okay, this input is A, this input is B, and let it be Y. Now we will check whether this Y will satisfy the expression for XOR gate or not, or we need to introduce one more gate, and then we will have some interesting conclusion. What is this A? A is appearing for this, therefore here I can write A. At the same time it is appearing for this. This is B, it is appearing as a input for this NAND gate as well as for this NAND gate. Because of these two inputs A and B, the output of this particular first NAND gate will be A dot B complement, and it is nothing but the output of corresponding NAND gate. In our previous video where we have introduced the NAND gate, we have mentioned that this is our NAND gate and the output is Y is equal to A dot B complement. Here it is AB input, A dot B complement. But for this second NAND gate, the interesting thing is that one input is A, but second input is A dot B complement, and therefore its output will be A, then the second will be A dot B complement, and then its complement. Now you may think about this in interesting manner. Suppose this is if I am representing this to be P, then the output should be A dot P complement. It is A dot P complement, but P is A dot B complement, and hence I have mentioned here it is P. For this third NAND gate, B is input, but first input is A dot B complement, and therefore somewhere here I will have to write it is A dot B complement dot B complement. Again I can say that if it is P, then P is appearing here. Therefore output of third NAND gate will be P dot B complement. This is P dot B complement. Therefore it is fine. And what about output of this NAND gate? Again it is very interesting. If I think about this entire to be R, this entire to be S, then the output Y will be R dot S complement. But how can I write R? R is nothing but, I will write the bracket. It is A dot B bar complement. This is R dot, what is S? S is A dot B complement dot B its complement, and then its complement. This is R, this is S. Now the De Morgan theorem is very interesting and it is very simple. Break the outer bond, change the sign. Therefore here it is dot, and on this dot there is bar. On this dot there is bar. Therefore I will have to break the dot, break the bond, and here I will have to change the sign, make it plus. The remaining A dot B bar, cha bar remains as it is. Break the bond, therefore this bond has been break. Here also I will have to write it is A dot B bar dot B bar as it is, and then I will have to write the bar. Now complement of complement, two bars are there over A dot B bar, therefore those bar gets cancel. Here also A dot B bar dot B, over that there are these two bars. Here I can insert a bracket for simplicity. Therefore these bonds gets cancelled. Further I can say that if I will have to break the inner bond, then I will write it is A dot A bar plus B bar, correct, check, plus I can write, see here it is break the bond and change the sign. Same here it is break the bond and change the sign. Therefore A bar plus B bar dot B, correct. It is very interesting. Now I will take a dot product with everyone as if it is dot, therefore AND operation with everyone. Therefore it is A and A bar plus A and B bar plus A bar and B plus B bar and B. Now let me know what about A and A bar. Suppose A is 0, then A bar becomes 1. Therefore 0 and 1, it is 0. If A is 1, then A bar becomes 0. Therefore 1 and 0 will be 0. Therefore for all time this will be 0 plus this will be A and B bar plus A bar and B plus this will be 0. And then finally I can say that if I add 0 or if I take OR with 0, the signal remains as it is. Correct? For example, I will represent here. Here it is our OR gate. Suppose this B is 0 and this A is only there, then it remains A because 0 will not affect the output, and hence this output remains as it is. It is A and B bar plus A bar and B. And interesting thing is that just we have observed that for a XOR gate, this is nothing but the Boolean expression, and hence I can say that this circuit behaves as the circuit for XOR gate. That means NAND can be used as a XOR. Here I will write, here it is NAND as XOR gate. Correct? NAND as XOR. Boolean expression will remain as it is. Truth table will remain as it is for the XOR gate, and this is the XOR gate with help of NAND gates only. This will be the fourth NAND gate. Now similarly, how to implement the XOR gate with help of NOR gates? Instead of NAND you will have to use 4 NOR gates, but check whether it will give you the same result or not. If you have any doubt, then contact me, because it leads to introduction of one more gate. I will not let you know what is the name of that gate. You may think about that, or if you contact me, then I will let you know. Thank you. This is about the XOR gate and how the XOR gate can be implemented with help of the universal gate, that is NAND gate. How to implement the XOR gate with universal NOR gate, that is the homework for you. Thank you.